Hello everyone, I am Dr. Osman reporting once again from the University of KwaZulu-Natal, the premier university of African scholarship. In today's lecture, we'll look at a practical application of element or atomic balancing together with energy balancing. And this practical application pertains to coal combustion to generate electricity. Okay, so we're looking at a double drum coal-fired boiler to generate high pressure steam, which is ultimately used to drive turbines. Okay, so you'll be introduced to the use of gross calorific value or high heating values and the calculation of combustion as well as heats of combustion, as well as various other factors such as the carbon usage efficiency, the overall efficiency of the boiler, as well as the thermal efficiency of our boiler. Okay, and finally we will look at the theoretical adiabatic flame temperature and how it's calculated and what is it actually relevant for. Okay, so there's very important parameters that need to be calculated and that have real and important use in the coal combustion to generate electricity. So we will be looking at one very large example to illustrate all of these points. Okay, so let's get straight to it. Now let's look at this practical example of using atomic or element balancing as well as energy balancing for a double drum coal-fired boiler. Okay, so this is a typical boiler setup to generate steam. Okay, so we have water coming in as liquid water, of course, and it's being passed through various pipes inside a furnace, and the furnace is of course generating the heat to change our water into steam, to vaporize our water. Okay, and in order to generate this heat, we have pulverized coal coming in as well as an airflow. Okay, and both the coal and the air is coming in at 35 degrees in this particular example. We have an air composition as follows: 21% air and 21% oxygen and 79% nitrogen. A pressure of 1 bar, in other words operating at atmospheric pressure. So we have combustion taking place in this furnace. We have ash coming out at the bottom. Okay, and as you can see, there's a conveyor belt system here to continuously remove the ash. And due to the fact that the combustion is not complete, we still have some elemental carbon coming out here together with the ash. Okay, so we have, that's our ash content and our carbon in the ash. Okay, and in terms of whatever is getting burned, the burning generates a flue gas, and this flue gas is typically at very high temperature, in this case 150 degrees, and it's this flue gas that's actually exchanging heat with the water in order to generate steam. Okay, and the flue gas consists of the following: nitrogen, CO2, SO2, water, and we are given an oxygen composition. Okay, and this example requires a few things of us. We need to find the steam production per 100 kgs of dry coal. So if we input 100 kgs per hour of coal, what is the steam production? We also need to find the carbon usage efficiency, the thermal efficiency of the boiler, the overall thermal efficiency of the boiler, and the theoretical adiabatic flame temperature. And we'll go through these terms as we go along, as we answer this example. Now we have been given some information. Firstly, we've been given an average CP value for the coal. We've also been given average CPs for the air and the ash. Okay, as mentioned above. And we also have been given the coal ultimate analysis. Okay, so 73% carbon, 0.6% hydrogen, 1% nitrogen, and so on. Okay, and it's also stated that there is some moisture in the coal. So 6% moisture by mass. And we have also been given a specialized gross calorific value formula, in other words, a high heating value formula. This is our QV that we've been talking about in the previous examples. So our QV is given as follows. Okay, now recall that the traditional equation for our high heating value made use of the total percentage carbon. However, in this specialized formula, we use only the burnt carbon. Okay, so the percentage of carbon that's actually being used in the combustion process. Okay, as you have seen, not all of the carbon is actually getting burned. We do have carbon in the ashes as well. And this is due to the inefficiencies of our boiler. Okay, so that's our GCV formula. And we can make a few assumptions, such as steady state operation, complete combustion of sulfur and hydrogen, combustion of carbon produces CO2, and of course some carbon will remain unreacted. And we can also assume adiabatic operation, in other words, no heat losses, perfect insulation. So there's no, in other words, Q is equal to 0. There's no heat removal to the atmosphere or any heat addition other than this combustion. Okay, so we have a perfectly insulated boiler. Okay, now once we've understood this information and these assumptions, we can proceed with our material balancing. Okay, and of course we don't know exactly what the reactions are, so it's a given that we need to conduct atomic balancing, right? Element balancing. And we can do this for each of our elements. Okay, so our elements will be nitrogen, carbon, oxygen, and sulfur, as well as an ash balance as well. Okay, and it's a simple case once again. Remember, for atomic balancing, it's simple: output minus input is equal to 0. If you want to write it in terms of net output flow rates, that's fine. Otherwise, it's quite simple enough to write it out as simply output minus input. Okay, so for our carbon balance, we will have carbon coming out at our flue gas in the form of CO2, and we have carbon coming in as elemental coal. We also have carbon coming out in the ash. Okay, so we can do a carbon balance as follows. In terms of our oxygen, we have 2 atoms of oxygen in CO2, 2 atoms of oxygen in SO2, 1 in H2O, and 2 in gaseous oxygen. Okay, so, and all of the oxygen comes out at the flue gas. We have an input of oxygen in the coal as well as the oxygen gas coming in. Okay, and we have all of our nitrogen coming in through our coal and our air, and output in the form of N2, and hydrogen coming in the coal and coming out as water, right? Water vapor. Now, it must be stressed that the balance between stream 3, 4, 1 and 2 is completely separate to the balance between stream 5 and 6. Okay, so stream 5 and 6 do not mix in the boiler. They do not mix with stream 1, 2, 4 or 3. We simply have an energy exchange between them. Okay, so we have pipes running and we have water inside those pipes, and those pipes are inside the boiler. So there's no actual contact between the water in stream 5 and the flue gases that's being emitted from the furnace. It's only an energy exchange, a heat exchange. Okay, so that's an important point. Now it's only necessary to actually perform the balance between streams 1, 2, 3 and 4, and we can achieve this quite easily for our carbon, for our hydrogen, for our nitrogen as well. Okay, so 2 atoms of nitrogen. Okay, and this is our output minus our 2 inputs. Again, for oxygen we have output, all in our flue gas. Okay, and that's minus our inputs. Okay, the same with sulfur. We have output of sulfur in the form of SO2 minus the input, sulfur in the coal. And finally, in terms of our ash balance, we can group it up as inerts and write out a balance. Okay, and once we write out this balance, it's a simple case of solving these balances either simultaneously or sequentially, and we will ultimately obtain the following flue gas composition as well as the stream 4 composition as well. Okay, there are a few complications when obtaining the total flow rate N3 as well as the nitrogen flow rate, but that's nothing that you haven't seen before. Okay, it's simply 3 equations and ultimately 3 unknowns, and so we solve. Okay, so that's the material balance covered. Now once we know what our material balance, once we know the results of our material balance, in other words, we know the flow rates of each component in each stream, we can ultimately now find the enthalpy of each component in each stream and perform an energy balance. Okay, and remember, our energy is being transferred from our combustion to our steam as well as wasted and coming out in our flue gas. Okay, now let's look at our energy balancing. We can choose a reference state for our enthalpy. Let's say 25 degrees and 1 atmosphere. Now the energy in the air plus the coal plus the heat of combustion is of course equal to the energy transferred to generate our steam. Okay, now let's look at our energy in the air. Okay, that's quite simple. It's sensible heat. We have air coming in, oxygen, at 35 degrees Celsius, and we can express that sensible heat in reference to 25 degrees Celsius using our heat capacities for oxygen and nitrogen. Okay, so here it is. Okay, so that's our energy in the air. Okay, we've been given the CP of not just oxygen and nitrogen individually, but CP of the entire air. So we can calculate our enthalpy quite simply. Okay, and now let's look at the energy in the coal. Okay, the coal is also available at 35 degrees Celsius, and we have also been given some information. Okay, we've been given the heat capacity of our coal. So we can find our sensible heat of our coal. Okay, in much the same way. we have 100 kgs of coal, so we can find the total enthalpy of the stream. Now, the CP of our coal was stated to be the CP for our dry coal. So in other words, the dry parts of the coal, excluding the moisture. So we need to count the moisture in the coal as well, and that will form part of the enthalpy as well. Okay, so we have been told that we have 6% moisture, and that moisture is of course water, so it's simply a case of finding the enthalpy of that water in reference to 25 degrees. Okay, and that accounts for a small enthalpy here, and so we need to total up the dry coal enthalpy with the moisture to give us the total enthalpy of stream 1. Okay, now we have also been given our ultimate analysis of our coal, and we have 73% carbon, 0.6% of hydrogen, 1% nitrogen, 0.3% of oxygen, 2.1% of sulfur, and 23% inert. Now for 100 kgs of coal, our total carbon is thus 73% times 100. Now, as you know, we have carbon that's actually, we have hydrocarbons that are being burned, and we have carbon that's of course coming out as part of the ash, okay, that's not actually burned. So we need to determine the difference, and since we've done our material balance, we can find our carbon in our ash, and thus we can determine the amount of carbon or carbonaceous material, in other words, that is being burnt. Okay, so the carbon in the ash in stream 4, we've been told it's 30% of stream 4, so we can easily calculate that. And we can find our carbon burnt. Okay, now once we have that, then we can ultimately use our GCV equation. Okay, now let's look at the GCV equation once again. Remember that this particular GCV equation used the amount of carbon that was burned, okay, not the total amount of carbon in the coal. So this is why we needed to find the amount of carbon burned. So now we can substitute it into this equation to find our GCV value. Okay, so we know the carbon burned is 63.14%. And we can substitute it into our GCV value. Okay, and you can confirm this and recall that from our previous lecture, our heat of combustion was given by the following equation. Okay, so that's our QV plus our different fractions of oxygen, nitrogen, and hydrogen. Okay, so this part here is our calculation of our GCV, and then of course adding my various fractions. Okay, so that will give us the heat of combustion of the coal. And now this is of course specific heat of combustion, so for our total heat of combustion, we simply need to take our flow rate of the coal. Okay, so that's our, so now we at this point we have established the enthalpy of the air and the enthalpy of the coal. Okay, not only the sensible heat, but also the heat that will be generated upon combustion, the enthalpy of combustion. Okay, now we can look at the enthalpy of stream 3 and stream 4. Let's look at the enthalpy of the ash first. We have been given our heat capacity of our ash, so that's quite easy to obtain. So that's for stream 4. And for our flue gases, our flue gas stream, we have also been given an overall heat capacity value. Okay, now in terms of our flue gases, we've been given the CP of our entire flue gas. Now remember that from 35 degrees to 150 degrees, our gases nitrogen, CO2 and SO2 remain gases. Okay, they remain as gases, so it's simple sensible heat. However, so we can quite easily sum up the enthalpies of each of these components here, our flue gases. But in the case of water, at 35 degrees, water is a liquid. So our moisture in the coal goes from being a liquid to being a gas. So in other words, it's gaining heat of vaporization. So we need to take that into account. Okay, so we're summing up our sensible heats for our gases excluding water. And then to express our water in terms of the reference of 25 degrees, we are going from 150 to 25, and if we use our steam tables, this is quite easily solvable. Okay, so now what we ultimately have found are the enthalpies of stream 1, 2, 3 and 4. And as you know, the enthalpy of stream 1, stream 2 and the combustion will be transferred to these pipes to generate the steam, and some of it will go out as flue gas and some of it will go out with the ash. So now let's look at our heat transferred for steam generation. Okay, so let's recap our enthalpies. Okay, so we have at stream 3, we have the following enthalpy coming out. And then we have energy in the air coming in, so this is stream 2. In terms of our coal, we calculated our heat of combustion and our total heat of combustion by taking into account our flow rate of coal is as follows. Okay, so this is our heat of combustion. I'm just going to label that C. And in terms of the actual sensible heat of the coal coming in, it was calculated as follows to be 1356, and this took into account our dry coal components as well as our moisture. And finally, of course, heat is lost coming out with the ash. So we have the following inputs of enthalpy from stream 1, stream 2 and our combustion. And we have enthalpy being lost in the form of the ash and the flue gas. Now the difference between our inputs and our outputs would naturally be transferred to our steam. Okay, so take a while to try and understand this, to wrap your head around this. We have energy coming in some of it is lost through the ash and through the flue gas. The remainder is being transferred to our steam in these tubes. Okay, so that's our energy transferred for steam generation. Okay, now once we know what our energy is, and we also know the inlet and outlet conditions of our water and steam, we can ultimately find our flow rate. Okay, now obviously our water coming in is equal to our water going out. So F5 is equal to F6. So we have a simple input minus output, or output minus input, being equal to QS. From our steam tables, we can obtain specific enthalpies at 1 bar and 35 degrees, as well as at 32 bar and 400 degrees. Okay, you can check this if you like. Go and confirm it by finding these values in your steam tables. And once we substitute this H6 and H5, and we of course have our QS, we can find F6. Okay, and that actually completes the material balance. Okay, so we used standard material balancing, okay, element or atomic balancing, to find our component flow rates in the coal, in the air, in the flue gas and the ash. And we used our energy balance to calculate the amount of heat transferred to this water to generate steam. And because we know the steam conditions and the water conditions, we can ultimately calculate the flow rate of the water and steam. Okay, so that's the first part found. Now what about the rest of these values here? The carbon usage efficiency, thermal efficiency of the boiler, overall thermal efficiency, and theoretical flame temperature. Okay, now these are typical parameters when it comes to coal combustion. Okay, so these are typical design parameters. It's very important to the fossil fuel industry, particularly in the combustion of coal to generate electricity. Okay, you'll find the same values being calculated for power plants that use natural gas as well as diesel or petrol. Okay, and this gives us an indication as to the efficiencies of our boiler. And once we know our efficiencies of our boiler, we can think of how we can improve these efficiencies. Okay, so let's first look at our carbon usage efficiency. Our carbon usage efficiency simply looks at our carbon in our coal and our carbon in our ash. Okay, so ideally all of the carbon in the coal should be burned to generate CO2. Okay, we ideally shouldn't have any carbon coming out with the ash. Okay, but in reality we will have carbon coming out with the ash, and we will have large amounts of soot forming here in stream 4. So we can quantify this. So our carbon usage efficiency is the carbon in the coal, originally in the coal, minus the carbon in the ash, divided by the carbon in the coal. Now this difference is ultimately equal to the amount of carbon that has been combusted. Okay, so we've already calculated the amount of carbon in the coal and in the ash, so it's a simple calculation to obtain our carbon usage efficiency of 86.5%. Okay, so that's our first parameter found. Let's look at the thermal efficiency of our boiler. Okay, now ideally all of our heat supplied by our furnace should be used for heating our water to generate steam. Okay, we shouldn't have large amounts of heat coming out in our flue gas or with our ash. Okay, because if energy is coming out as flue gas, remember this flue gas is just being emitted into the atmosphere and this ash is just being recovered. So if we have large amounts of energy coming out, this is ultimately energy wasted. Okay, so ideally we would want all of the heat generated in this furnace to be used in heating up our water to generate steam. Now we can quantify this. The thermal efficiency of the boiler is equal to the heat transferred divided by the heat supplied. Okay, so we've calculated the amount of heat transferred to generate steam, and it was found to be the following. Regarding the heat supplied, let's look at our supply. We have heat supplied as sensible heat with the coal, sensible heat with the air, and heat of combustion. So that was our heat supplied. So quantifying our thermal efficiency, that is defined as heat transferred over heat supplied, so it's an easy calculation, and we see that the boiler is 93.6% efficient. Okay, now let's look at the overall thermal efficiency, which is different to the thermal efficiency of the boiler. Okay, the overall thermal efficiency is equal to the heat transferred divided by the maximum heat supplied. Okay, now the maximum heat supplied would occur if all of our carbon was burned. Okay, so remember that ideally we want all of our carbon in this coal to be burned. But now we have carbon losses in reality to the ash. So let's calculate our heat input if all of the carbon was burned. In other words, let's calculate the maximum heat of combustion. Okay, and as you know, before we had the GCV value, and this was found by looking only at the amount of carbon burned. We had 73% of carbon in the coal, but only I think 63% was actually burned. So let me see if I can find that equation again. Okay, there it is here. Previously we've looked at our heat of combustion and we've calculated our GCV by looking at the amount of carbon burned rather than the total carbon in the coal. Okay, so the amount of carbon burned was only 63.14%. So now we are finding the maximum heat of combustion and considering the full 73% of carbon in the coal. And so now we obtain an alternative value. So our maximum heat supplied is now equal to the following. Okay, our inputs of coal and our air remains unchanged, but now we have a higher heat of combustion. Okay, so now we have the following. And we can use that to ultimately find the overall thermal efficiency. Okay, and the overall thermal efficiency is 80.6%. Okay, now it's very important to get these definitions correct. Okay, make sure you understand them well. Okay, lots of students take these definitions for granted. Although they are simple calculations to make, it's very easy to get confused between the thermal efficiency and the overall efficiency, as well as the coal combustion efficiency. Okay, so it's very easy to mix them up. Make sure you get them right. Okay, and now finally, let's look at the theoretical flame temperature. Okay, also known as the adiabatic flame temperature. Okay, now the theoretical flame temperature results from the energy balance written for the furnace only. Okay, in other words, before the flue gas reaches the steam generator. Okay, and in such a case, the energy in our air plus the energy in our coal plus our heat of combustion is equal to the heat loss in the ash, the latent heat to vaporize the coal moisture, and combustion water at 25 degrees plus the sensible heat to raise the flue gas temperature from our 25 degrees to our flame temperature. Okay, so what we are doing here exactly is, instead of performing a balance over this entire boiler, we are considering simply this portion here. Okay, so we are now neglecting this water streams here in order to heat up the water to the steam. We are neglecting this. Okay, so we're only doing a balance on this little box here. Okay, and we can do that to find our theoretical flame temperature. Okay, and this will give us an indication as to what the temperature will be immediately emanating from this combustion. Okay, so now let's look at our balance. Okay, so we have our coal coming in, and that includes the dry part of the coal as well as our moisture in the coal, our water. We have air coming in with an associated enthalpy. We have ash leaving, and we have flue gas being emanated here, and we have heat generated as a result of our combustion. Now remember that only the dry part of the coal, the dry components of the coal, are actually being burned. The moisture in the coal is simply, that's your water, and that actually needs to be heated up to generate water vapor. Okay, so these are things that we need to take into account. So here is my enthalpy coming in with my coal and with my air, and this is the heat generated as a result of combustion. Okay, now this is the enthalpy coming out with the ash, and this here is the enthalpy to vaporize the moisture in the coal. Okay, and as you can see, it can be quite substantial, which is why we prefer to have completely dry coal rather than coal containing any moisture. Okay, so it requires a lot of heat to vaporize our water. And finally, what's leaving out of this furnace is our flue gas. Now, the flue gas leaving the furnace here will have a different enthalpy to the flue gas leaving out here, because from our enthalpy here of our flue gas, part of that enthalpy, part of that heat will be transferred to these pipes. Okay, and the result afterwards will be our flue gas coming out here. So this flue gas here, the enthalpy of the flue gas coming out here, will obviously be a lot higher than the flue gas coming out at the stack. Now we know our heat capacity, so it's simply a case of finding our flame temperature. Now if we have an average heat capacity, it is quite an easy equation to solve for TF. However, if my heat capacity values are of course long integrals with our coefficients a, b, c, d and e, then we will end up having a fifth order equation which we will need to solve, and this will of course will have to be solved iteratively. Okay, so the suggested method will be as follows. We could guess an adiabatic flame temperature, let's say for example 2000 degrees. Then we perform our calculation and we find our new flame temperature and calculate our new enthalpy, and finally our new flame temperature again. Now we repeat this until our flame temperature is equal to the previously calculated flame temperature. Okay, and you can do this using the Newton-Raphson technique if you want to do it manually, or you can do this using software such as Solver and GoalSeek in Excel, right? Microsoft Excel. Okay, now what we end up finding. Okay, so that's our final adiabatic flame temperature, and this is called the theoretical adiabatic flame temperature because we are assuming that there are no heat losses to the surroundings. Okay, so in other words, perfect insulation of the furnace. Okay, so it's very important that you review these definitions. Okay, the carbon usage efficiency, thermal efficiency, overall thermal efficiency, and the theoretical flame temperature or adiabatic flame temperature. Okay, so that's the same thing. And once you are well acquainted with the definitions, then actually calculating these values can be quite simple. Okay, so that's the problem solved.